Hello, everyone. Today we will continue our lecture about Introduction to Data. So the last time we have covered basic databases and data types. So we have discussed relational databases as well as unstructured databases and databases that come in forms of graph and chemical structures of data, as well as some biological data and climate data. So those would have their own format in addition to relational databases. We also discussed the types of data that exist in terms of when we are creating the database, we have to specify the data type for the values of the data or the attributes that we are creating. So we also mentioned that the attributes are also called descriptions or features because they describe the objects. And in a relational database that comes in form of table, those are on the columns, while the objects are on the rows. We call those objects or records. They can also be transactions, but we call them objects because they can be anything. Now they can be humans, for example, customers, students, or patients in a hospital, or they could be transactions, or they could be climate data, or they can be tumors in a medical database. So for that reason, these are called objects, what we have on the rows. So that was about relational databases, and the data types that we discussed were the nominal and numeric and numeric and qualitative, which can be text, but they are not numbers. But they could have properties such as being ordered or being able to be divided or multiplied. So based on those properties, we discussed the data types that exists. So today we will continue about the data and basic data analysis. So there is a way to analyze the objects that exist in the data. And for example, if the data objects are customers of a bank, we could do some comparison between those objects. So that is, we can tell this particular customer is similar to another customer. Why we would want to know that this customer is similar to another customer? It's because this way we can find groups of similar objects. We can find customers that are profitable for the bank, or we can find customers that are non-profitable, or we can find customers that are neutral. That is, so by determining the similarity between the objects, we can learn a lot about the objects. So we can find groups of similar objects. So that allows us to do allows us to do data analysis on those objects. So the similarity is a numerical measure of how alike are two data objects. Dissimilarity will be the opposite of similarity. That is, it will show how much they are not alike. So let's say if the value that we are measuring is between 0 and 1, and if the similarity is 80%, for example, or 0.8, if it's between 0 and 1, then the dissimilarity would be 20% or 0.2. So the dissimilarity is the opposite of the similarity. So this will be a value between 0 and 1. Another thing here that is important is that the distance between the objects, proximity or distance, which is also related to the similarity and the dissimilarity. So proximity will be when the objects are similar to each other. If we are to plot those objects, that is, we're going to visualize the objects in a two-dimensional space or three-dimensional space, as many attributes as they are, each one of those is a dimension. If we are to visualize the objects in space, then we can measure the distance between those objects. So the ones that are similar to each other are going to be close, in a close proximity from each other. That's why we say we create groups. We can actually visually see those groups as circles or clusters on the plot. Over here we have group cluster 1, over here cluster 2, and over here cluster 3, if we are to visualize them. So in that circle are going to be all the items or points that are close to each other. And so why? Because when they're similar, their attribute values are almost the same. So if we are to plot them on an XY coordinate system, they end up in the same spot. So that's why they're close to each other too. Now, the ones that are very different from each other will end up in a completely different place on the plot. But they will be together with other similar objects like themselves. Okay. So this is an easy way to analyze the objects. So we mentioned that the types of values that we can have in the database can be nominal, ordinal, or we can have interval or ratio. So similarity and dissimilarity can be computed for these objects. Now, if we are to use certain formulas for computing similarity or distance, we would prefer to do this with attributes that are numeric, because we can easily add and subtract them to find the distances between the objects. If they are not numeric, if they are text or picture or sound or something like that, we can convert them to numeric, that we can normalize the data, or we can map them into a numeric value and record that instead, so that we can compute the similarity or the dissimilarity. But what this is basically showing is that the similarity is between 0 and 1, and the dissimilarity would be 1 minus the similarity. So if it's between 0 and 1 and similarity is 0.8, 1 minus 0.8 will be 0.2. So it is basically showing similarity is 1 minus the dissimilarity. So, like I said, it will be easiest if we use numeric values. So if we use numeric values, we can easily compute things like the Euclidean distance. So the Euclidean distance is really the distance that we know in our everyday life. If we are to compute, if I start drawing some points on a whiteboard in a coordinate system, and I take a ruler, I can measure how far is this point from this point. It's about 2 centimeters or 1 centimeter. Or I can measure the distance between two cities. Can we measure the distance between Irvine, California to Los Angeles, California? We can measure that in miles or kilometers. That's also Euclidean distance. So this is the distance that we are known in everyday life. The way it's computed is by using these formulas. If we have values for our objects, and if they are two attributes, X and Y, we are dealing with, no, X and Y are the points here, the objects. If they are two attributes, then we are dealing with two-dimensional space, and K is going to be equal to 2. So K here is the number of attributes that we are having to measure. And then we take, so we're going to subtract the value for the first attribute minus the value for the second attribute. The first object, value for attribute 1 for object X. Subtract that for value for attribute 1 for object Y. Then square it and take a square root of it. And we're going to add to this the attribute 2 after that, if we have two attributes. So we're going to subtract the value of attribute 2 for X from the value of attribute 2 for Y. If we have more than 2 attributes, we will keep adding those here. That's why we have this summation, K from 1 to N. So as many attributes as we have, we're going to add them together. And that gives us the Euclidean distance. So here's the situation. We are plotting the data objects into space. So here we have points 1, 2, 3, and 4. We have 4 objects, but so how are we plotting them? We're just taking the coordinate system. In this situation, we have 2 attributes. The first attribute will be plotted on the x-axis, and the second attribute will be plotted on the y-axis. So this is x, and this is y. So the x goes here. First point for x, it has 0. So it's right here. But for y, it has 2. 1, 2. So that's why point 1 ends up exactly in this location. In the second object, point 2, for x, it has a value 2. So going on the x-axis, you go to value 2. But for y, it has a 0. So that's why 0 for y. The point ends up in this location. Now, point 3 has a value 3 for x. So 1, 2, 3. Point 3 is over here. And value 1 for y. So y is 1. Point 3 ends up over here. And point 4 also has 1 for y, but it has 5 for x. So this is how we're going to visualize the data into space. So the objects that are similar to each other are going to be close to each other. So for example, the point 2 and point 3 are similar to each other because point 2 x is 2, point 3 x is 3. So they only have 1 unit difference between the value of x. This one is 2, this one is 3. Same situation for y. The value of y for point 2 is 0. The value of y for point 3 is 1. So they only got 1 unit difference between both the x and the y values. So those are close. These 2 points are the closest to each other from any other points on the data, on the plot. So the points that are close to each other are going to be similar to each other, and they can end up in, if there's a lot of points, they're gonna end up looking like a circle or a dense spot on the plot. So these are going to be clustered together. We can say this is cluster 1 here. Cluster of similar objects. So if those are customers, these could be both, these are students and both are master students, for example. The other guys could be working adults that are not students, or they can be children that are in kindergarten. So that's to make a difference of, to give an example of what that means. But we can compute the distance between all the points in our data. And if we do that, we would create what's called a distance matrix. So this distance matrix can be used for data analysis. It'll show the difference between all the points in our data. If we are to take the distance between point 1 to point 1, the distance is going to be 0 from the point to itself. That's why we have a 0 here on the diagonals, because these are showing point 2 to point 2, point 3 to point 3, the distance from the point to itself. Now, if we're to compute the distance between point 1 and point 2, we're going to go back to our formula that we have here. So we will plug in the numbers for the first attribute and the second attribute and subtract them. So let's say we're going to subtract a 2 minus 0 and check and square that. So 2 minus 0 is 2. And then the same for y. 0 minus 2 it's going to be minus 2, but because we square it, there are no negatives. And so once we add those together, take the square root of it, we get 2.82. So the distance between 0.1 to 0.2 is 2.82. So we can compute the distances like this between all the points in our data. The top of the table is the upper part above the diagonal. The numbers are the same as the numbers below the diagonal. So we really only need half of this matrix. We're going to use the bottom half that's below the diagonal. There are many distance measures. We started with this Euclidean distance because it's the most intuitive. It's the one we understand in our everyday life. Like I said, if I come here, instead of using this formula, I take a ruler and measure this distance. I can measure 2.8 inches here, for example. Or if these are two cities, I can measure 2.8 kilometers between them. That's Euclidean distance. There are other distances. If we tweak the numbers here, let's say instead of taking power of 2, we take power of 1 or power of 3 or a power of 4, then we end up with a different distance measure. So here it shows power of r instead of 2. So that's just to say that we can choose different powers here. So that would be called Minkowski distance. So CT block is when the r is 1, that is, we're taking power of 1. That's also called Manhattan distance or CT block distance. If we take power of 2, it's Euclidean distance. We can take power of 3, power of 4, or infinity. If we take infinity, then this is the maximum difference between any components of the vectors. This is just to give an illustration of if we take power of 1, power of 2, what happens? So we end up with different distances here. So Manhattan distance is different than Euclidean distance. So really we need to choose the distance that is the best for our data and for the goal of our analysis. But the data that we were showing here had only 4 objects. As we can imagine, our data is going to have a lot more than 4 objects. So if we plot all of them in space, we might end up with something that looks like this. So there are other distances like Mahalanobis distance, which is using a matrix here. Something important that needs to be noted is that if we have binary data, this Euclidean distance really doesn't make much of any sense because if we have binary data, we only have zeros and ones. And we can add them and subtract them and take the square root of them, and that doesn't have much meaning for binary data. So for binary data, we need to use something different to compute the similarity. So we use something called Jaccard coefficients. So these would allow us to compute distance for binary objects. If we are comparing two values, and so let's say the value for attribute 1 for the first object and for the second object, that's two values for attribute 1, first object and second object. The value can be either 0 or 1. So we have 4 possible combinations of two values, which can be either 0 or 1. We can have 0, 1, 1, 0, 0, 0, or 1, 1. These are all the possible combinations. So if we take the first one, let's say the value for first object is 0, but for the second object is 1. This would, that's the first coefficient. So I was just giving example with one attribute, but if we're to do this for all of the attributes, we can simply count the number of attributes where we have this combination 0, 1. So number of attributes P is 0, Q is 1. And the logic is the same for the remaining combinations. We're going to count for F1, 0, we would count number of attributes where we have 1, 0. For F0, 0, we will count number of objects where we number of attributes where the both objects have a value of 0. And the last one is number of attributes where both objects have a value of 1. And so once we have recorded those for the whole data, we can compute similarity between objects for binary data. So the Jaccard coefficient will take F11 plus F00 and divide it by summation of all of them, all the combinations. This is called Jaccard coefficient. So for example, in this situation, there are two objects X and Y, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 attributes. So this is essentially a vector. We are comparing two vectors here. We're going to count the number of attributes where the first one has a 0 and the second one has a 1. The only place we have that is right here. The first one has a 0 and the second one has a 1. So we got one of those. So F01 is 1. Oh, actually, there's two of them. There's one more right here. So we're supposed to take F01 over here in the formula. So as you can see, that's equal to 2. So there's two of those. Then we count the number of attributes where P is 1 and Q is 0. So there's one over here. We have 1, 0, Well, there's one of those. The number of attributes where P is 0 and Q is 0, we got quite a bit of those. We have all of that. All of that. So there is 1, 2, 3, 4, 5, 6, 7 of them. So that's where you see the number 7 here. And for the last one, it's 0. We don't have any that have both of them at once. So if we compute the Jaccard coefficient between those, we would get a 0.7. I mean, this is the, sorry, simple matching. Sorry, the first one is called simple matching, SMC, and the second one is Jaccard. So in simple matching, we'll get the similarity 0.7, while Jaccard will get a 0. And the last thing here, we have a cosine similarity. So the cosine similarity is using cosine in the formula. And here's an example, two vectors of how to compute the cosine similarity between them. So it will be 0.315 if we follow this formula here. So there are a number of distance measures that we can use. They essentially all will show the distance, which is the objects that have bigger distance have a bigger dissimilarity. The objects that are close to each other have smaller distance, they're more similar to each other. The way we know they're close or far is if we plot them in space, we can visually see where they are. And we can tell like this one is far from that one, while this one is close to this one. The way we measure the distance or the similarity, we have seen several measures. We need to choose, we need to decide which one to use. So the way we choose that is depending on what kind of data it is. So the domain of the data what kind of data? Is it medical data? Is it educational? Is it some sort of industrial data? Depending on what it is, and the goal of its application. So what is our goal in measuring the similarity? So we can based on our goal and based on the types of data that we are dealing with, we need to choose the best, we need to choose the appropriate similarity measure. So measure must be applicable to the data and produce results which are in sync with the domain or the application of it, of this data. Okay, so we will go up to slide 54 today. And the next time we will continue with information-based measures, such as the entropy.